Hi guys, welcome to the week 7 solutions video for the Newton's laws questions 14 and 16 and the momentum and impulse questions 19, 20, and 21. So why don't we get started here. At any time you guys can skip to any particular part of the questions that you want to see the solutions for. Okay, you can just do that through the scroll bar. Find the time code that matches the question you want to look at. So let's start with number 14 here. Emily is skiing on a hill, so a slope in blah 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 blah, where the slope is 17 degrees. So why don't we draw a little diagram to represent that? Okay, so this is 17 degrees. There's the slope. I'm just going to draw a free body diagram to represent her. I know at this point she's got 60 kilograms. Okay. And at one point she's moving downhill at constant velocity. Okay, so she's moving this way. That's her motion at the moment. Calculate the value of the dynamic friction. Okay, so the friction would go the opposite way of that. I'm going to label that FF. On the skis at this point in time. Okay, so first of all, we have to look at the forces that are going on here. Well, if she's moving at a constant velocity, all forces in the same plane, then in this case where she's moving down the hill, okay, we're going to call that just the force downhill in the x direction. All right, that just means it's following this plane going that way. So if she's going at a constant velocity, then that means if v is constant, then that means for us F net equals 0. F net in the slope direction is 0. Okay? So, okay. Then how do I know that? F net is what? Well, it equals Fx, the force of whatever in Fx, plus the frictional force. And we can see that one's negative and one's positive. Well, first off, we don't know these ones. We actually want to find FF. We want to find that, so that we don't know. We do know the net force must be 0 because the velocity in that direction is constant. So how can I get Fx? That's the only thing I had to know that first to solve for Fx. So in this situation, we're talking about a mass affected by gravity, and so let's take a look at the forces acting on this. It's not just those two forces. In fact, we have two other ones on this, and that is gravity, okay, Fg, which we know is mass times the acceleration of gravity. And because this skier is on a surface, we also have this force, the normal force, okay? And in fact, it's those two that end up creating this force that pushes the skier down the slope. Okay, all right. So I'm going to just redraw this so it's more comfortable and we can see it more clearly. So we have a vector diagram to represent mg, the weight force, and then we're going to have a vector to represent the normal force. Okay, I didn't draw that very clear. That's more realistic there. Okay, now it's saying that I just said it's the gravity and the normal force of the surface that actually creates the force that causes the skier to go down the hill. And then so the net force starts at the first vector here and goes to the end of the second vector. See, the vectors all follow a path. Okay, so that's going to be my Fx, and you can see it actually follows this angle of the slope. And it's going to, then where exactly is this angle then? Well, that angle, if it's relative to a horizontal plane to our slope, then that one, well, it goes opposite the angle of the side that we want to find, which is fx. And it's the net, that's the net force here of these two forces. Okay? Don't confuse it with the net force of this x horizontal force and the frictional force. We just want to find fx first so we can solve for this. Okay? Okay, so in this case now, well, we don't know normal force. Normal force is actually the reaction force of the gravity force from the surface. We do know mg though. So how do we know mg? Well, fx is a component of that. If I were to break down fx into its horizontal and vertical component, I can see one of them downwards matches the same direction as gravity. And in fact, is that gravity that is part of this. Okay? So this fx then will be the component of the gravity, but if I draw it as this vector, I can tell that, oh, okay, it's sine 17 because it's the side, the vector across from the angle. All right, so once I know that, I can put in the information I know, the gravity force, and then the sine 17. Anytime you have a slope problem where you have given an angle and you want to find one of the components that's made from other vectors, draw a vector diagram like this, put the angle in the right spot, and then following trig rules, because the normal is perpendicular to this fx, then it creates a right angle triangle, and from there we are able to solve for fx. Fx then would be 45 times 9.8 sine of 17. Okay, I can close this, I don't have to. And it gives me 129 newtons. Okay, I'm just going to keep that in my calculator. I'm going to write that there. So, again, if I want to find FF, then basically I need to hold on, let me expand this a bit. Okay, rearrange my formula here to solve for it. Okay, Fx equals F net minus Fx. And you'll find that this gives you a negative answer. We know F net is 0, so minus the 129, and so it equals negative 129. And that negative just tells us that the force of friction is opposite it. Oh, not 0. What's with the 0? That's an N. Okay? And there it is for 14. Let's move on to number 15 here. Okay, so the question is, 16, I'm sorry. 16. A truck of mass 270 kilograms is towing a trailer which contains rubble with a total mass of 1,300 kilograms. Okay? If the engine is supplying a force of 8,000 newtons, calculate the tension in the tow bar. Okay. Fantastic. Okay, so what do we know? We'll just highlight the information we know. Mass of the truck, okay, we'll just call that M1, is 27,000 kilogram, 7,700. Towing a trailer that has a mass, so mass 2 is 1,300 kilogram. And then the applied force that we have is 8,000 to the right. Okay, calculate the tension in the tow bar. So here is our tow bar. Okay, that part there, right here. And that's going to pull this way. So that's tension force. Okay, it's going to pull this. Now, how are we going to determine that? Okay, first of all, we need to know what the applied force here is. Okay, so to find the tension, we have to come up with a formula that matches everything. Okay, so what we know so far is that the applied force is for both the truck and the trailer here. So the truck and the trailer will be pulled by the truck, just the applied force from the truck's engine. Okay, so that we know, and we know the masses of both of them, and the tension is another force in itself. Now, the thing with the tension is there's only tension if there's a load on it. So you'll notice that the tension of this tow bar is due to the mass of the trailer behind it. Okay, if there's no mass of the trailer, there's no tension in the tow bar. So we have the engine creating a force this way, and it's pulling that mass. And then the tension here is a force that's pulling this mass. So what is common about these two things? There's got to be something common. If we look at the masses of the two being pulled by this, okay, and if we, I guess there's no reactive force, there's no friction, there's no air resistance, so really the applied force is the net force. And we know that net force causes an acceleration. Okay, so if we rearrange this, what happens is the net force, or the applied force, okay, of the engine then divides by the total mass. And if we plug this in for what we know, which is 8,000, divided by the mass of the two, because the engine is pulling both the truck and the trailer. So that is 2,700 for the truck and 1,300 for the trailer. So what we end up with is, well, if I go to my calculator, 8,000 divided by, and if you see, if you're good at math, you can see that would be 4,000 underneath there. But I'll just show you here. If we need to show it on a calculator, so there's no mistakes, you should get 2 meters per second squared. Okay? Now, the truck and the trailer are both accelerating at the same acceleration. So, if this trailer is accelerating at 2 meters per second and it's only 1,300 kilograms, then that means there's a different force on it. Okay? How much force is pulling it? Well, we can see this now. That tension force then is the net force. Okay, so I'll just write that there. And it equals the mass times the acceleration. So this mass is accelerating. How much force did it take to do that? So I'll just put that in. This is mass 2. Okay. So that's going to be 1,300 for the trailer, and then 2 for the acceleration. And we can see that if I use my calculator, I don't think you need it for something such as that, but I will put it in. Okay, so it's 2,600 newtons is the tension in the tow bar. All right. I think our next question is from the um, moments and not moments, sorry, momentum and impulse, right? So let me go back here. We're done with that one. We'll go to momentum and impulse here. And I think we're doing 19, 20, and 21. So let me zoom in here. I need to open it up so we can see it. Okay, great. So we start off with 19 here. Okay, so first thing we'll read it and, highlight our information. Okay, so we have a basketball, 400 grams thrown downwards. Okay, at the ground at U, okay, M, and then rebounds at a velocity of 8 meters upwards. Okay, so there's V. Okay, what is the change in momentum? Okay, so change in momentum, we have U, we have V, we have the mass. The change in momentum would be the final velocity minus the initial velocity. Okay, if I draw this, what happens is on the way down, we would say, let's say that's the positive direction because that's the initial direction. And then the bounce up would be then negative direction. Okay? So that's going to affect our numbers in here. In what way? Well, the mass stays the same. In fact, I can even factor out the mass so that the 400 grams, our mass is 400 grams, which is really in kilograms, 0.4 kilograms. Okay? So we'll have that here. We'll just take that out because we can see it's common in both those as a factor. So it's going to be V minus U. But from our V minus U. Yeah, okay. So our final velocity is upwards. Now, it depends on which way you decide is positive and which one is negative. It doesn't matter, but in the end, you'll see it'll come out the same anyways. All right, so velocity, the final velocity was upwards, and we say that's negative in this situation, all right? Minus, what was our velocity? Going down, 8.5 going down, okay? Okay. So in the end, once we get our calculator out, it'll be 0.4 times negative 8 minus 8.5. Okay, and we can see there is a negative value to the change in momentum. That makes sense. The momentum changed direction, right? The direction of the velocity was up when initially it went down. So it makes sense the momentum is a negative value, okay? Okay. Kilogram meters. And that just says it's up. Or you could just say 6.6 meters per second up. Okay? It really depends. You could have made the initial direction negative here, and what would have happened was the answer would have came out positive, and that would have made, upwards. If you made up positive, it would have matched it. Okay. What happens if the ball was in contact with the floor for 250 milliseconds? What was the force exerted on it? Okay. So the ball, we have time equals 250 milliseconds, which we know is really 0.250 seconds, real seconds, milliseconds. What else do we know? We know the change in momentum from the previous question. Okay. So I'm just gonna go change in momentum. Yep. 6.6. I'm not gonna write out all the units again. You guys know the units, they're up here. It's up. So the force, as we know, okay, change in momentum. We also know change in momentum equals impulse. And impulse is the equation that involves force and time. We want to know force, right? So that's going to be force times time. So let's solve for force. So in our equation, we're going to rearrange this, and we're going to have impulse divided by time equals force. Okay? So next step, we have 6.6 divided by 0.25. And that's going to equal, well, 6.6 divided by, I still have it in my calculator, so I'm just going to use that. And that just tells me it's up again. Remember from the original one? We could include the negative if we wish, but I think in this situation, I probably, in hindsight, should have made up positive. Okay, so it's 26.4 newtons, and that's up. That's the floor exerting force on the ball. All right, part C. In this collision seems to contravene Newton's idea that no net momentum change occurs in any collision. As the ball has had a momentum change, discuss your ideas. Well, sure. The ball hits the earth, right? And so you would think the ball will go one way. Ball goes up. Earth goes down. But because the mass of the earth, the mass of earth is so massive, is so big, we don't really see it move. We don't see it move. We don't see it change its momentum. Okay? That's essentially C. All right. Okay, we're going to move on to the 20. Okay? What we have is a jet of water strikes a curved blade, this turbine blade here, at a speed of 25 meters per second, and returns in an opposite direction of 24 meters per second. The mass of the water striking the blade per second is 41 kilograms. Okay, so we know some information. We know U is, we're going to write it here, I guess. U is 25. And if we make this positive, then it depends on U which direction is positive, which direction is negative. So we got to determine that at the beginning. And then V then would be negative 24. And they're both meters per second, of course. Okay. What do we have then? Then we have the mass is 41. Okay. Kilograms. Okay, so first of all, what is momentum? Well, calculate the force exerted on the signal by the water. So if we know change in momentum, As we saw in question 19, part C, change in momentum or impulse involves force. So, how can we find this one? Okay, if you start with this, then we can say change in momentum. Well, it really determined by the mass stays the same, so really it's the change in velocity times the change in momentum. I just shortened this a little bit, but we know this is 41, and we know the velocity is negative 24 minus, is it 25? Yep, 25. Okay, making sure I have everything in there. So in the end, we get change in momentum equals 41 times negative 24 minus 25. It'll be 49, it looks like. Okay, so 2009 kilograms meters per second. Okay, so we have that. It's about 2,000. Calculate the force on it. Okay. Well, calculate the force exerted on the blade. So how do we do that? Well, this is the change in momentum per second, right? Because we have kilograms per second. So therefore, IE equals F times T, but T is already 1 second. So the change in impulse is the force. So there we go. Force equals 2,000. We can't ignore the negative for now because it only asks us for the force exerted by the blade, or on the blade by the water. So that's it. You see? Okay, so every second there is 2009 newtons of force. If I make this 3 significant figures like I should, then you should end up with just 2.00 times 10 to the power of 3 newtons, okay? And you just round that off to 2. If the whole, let's say do part B, if the whole turbine consists of 55 blades, each a mass of 250 grams, calculate the accelerator from which the blades recoil under the impact of the water. Okay. So what should we do first? We have 55 blades. Calculate the accelerator which will impact the water. Okay, so we have the blades and there are 55 of them. So let's find their mass. There's a reason why they tell us how many there are and that each one is 250 grams. So 250 grams we know is 0.25 kilograms because we need to convert it to kilograms. Okay, so that's 55 times 0.25 each. And we should get 13.75 kilograms for the total mass of the blades. So we're just assuming every single one of the, if we assume every single one of those blades is getting hit by water every second, then we can know, we already know the force every second. So what's the acceleration? This one's kind of easy. We're going to rearrange our net force, our force divided by mass. So we got 2009 if we use that one, divided by the mass. Okay, and we should get some number. If you use 2000, that's totally fine as well, because really that's how you should write out the final answer. And so there is the acceleration. Okay, we should get 146. Yep, that's it. 146 meters per second squared. Okay, and that's part B. So question number 21 We'll just read through here, underline the information we know. Okay, so there's a man, we'll call him mass 1, he's 90 kilograms, and he's standing on the front of a boat, and that boat is a certain distance away. It's 0.5 meters from a jetty, and the man tries to step onto it by moving forwards at a speed of, I don't know, 3 meters per second, so we're going to call that V1. In this case, V1, U1, we're going to say U1 then. The boat has a mass of 180, okay, we'll call that M2, and then moves backwards as the man moves forwards. Okay, so we have a velocity, another velocity 2, all right? Sorry, change that to U. Okay, so we have two velocities, two masses, and the question says, explain why the man moves towards the jetty at less than 3 meters per second. Well, for us to do that, let's see what we understand about the question first, right? For the man and the jetty, maybe we draw a little diagram to help us. So we have the boat, we have the man stepping off the boat towards a jetty. And a jetty is like just a dock, like this. I'll just draw a little better. Whoops. Okay, it's in the water. So he's going to go this way, 3 meters per second. And the boat's going to go this way because according to Newton's third law of motion, that for any action there's equal and opposite reaction. So for the man to move forward, he's got to push on the boat, but because the boat's in the water, the boat's going to move backwards. Okay? We already know the mass of the boat. We know the mass of the man. But before he starts his motion, the boat and the man are not moving. Okay? So that means they're, according to the law of momentum, they start off at pi, or their initial velocity is 0, or the initial momentum is 0, so that means it will continue to be 0 once he tries to step off. So that means the man and his velocity plus the boat and its velocity, I keep writing v, don't I, will equal to 0. So what if we replace it with the information we do know now? Okay, so we know M2, we know M1, we know V1 is 3, and then we're going to actually find what V2 is. Because V2 is going to help us explain why the man steps off the jetty at less than 3 meters per second. Okay? All right, so let's start off with this. We're just going to substitute our values in, and so let's do this, why don't we? Okay, so for man, we have 90. His velocity is towards the jetty. We're going to say that direction is positive. Okay, should have done that at the start. So that's 3. Plus the mass of the boat, which is 180, and that's going to multiply the velocity of the boat. And all that's going to equal 0. So our next step, we want to solve for just the velocity of the boat. So we're going to go here, and if I move this over, all that move over to that side, and it'll be divided by 180. Okay, it's just some algebra here at this point. So 90 times 3 divided by 180. Okay, and not only that, but this becomes a negative value, and this is going to really help us understand what's going on with the direction too, because we know the boat is going in the opposite direction of the man, and we already said the man's direction is positive, so it makes sense our answer is going to be a negative answer. Okay, so if you did this, if I took out my calculator, I mean, you can do it in your head, I'm sure, guys. 270 is 90 times 30 divided by the 180. You can see there's a ratio there, 3 to 2. If I did that, you can see it's 1.5. Okay, so 1.5 meters per second backwards. I can say negative 1.5 meters per second, or I can say 1.5 meters per second backwards. So if the man is giving some momentum to the boat by increasing its velocity, then the man's momentum will have to decrease. So therefore, his velocity will be less. Okay? All right. That's what you can explain. You can explain that due to conservation of momentum, if the boat gains momentum, then that means you have to take away momentum from the man to continue to have conservation of momentum. All right, let's do part B. If the man maintains his forward velocity for a period of 0.3 seconds, so we have time there, determine whether the man can successfully step onto the jetty without falling into the water. Yes. So first of all, we should really know what is the velocity of the man. Remember, the boat is moving backwards. So the boat is moving backwards at 1.5 meters. And the man is moving away from the boat, it says forward at 3 meters per second relative to the boat. That's a huge hint. So his velocity is 3 meters per second to the boat. But the boat is already moving away from the jetty at 1.5 meters for the boat. So in reality, the man's net velocity is 1.5 meters. How did I get that? Well, he's going to the right at 3 meters per second, but the velocity of the boat is negative 1.5 because it's in the opposite direction. So the man is really only moving towards the jetty at 1.5 meters per second. If that's the case, then what happens is we can find his displacement in that time because it's v times t, right? That's his velocity. So 1.5 times 0.3. I don't really need a calculator for this, but I will do it one more time. 1.5 times 0.3 should be 0.45. Yes, 0.45 meters. And we can see, therefore, it's much less than the 0.5 meters the boat is away from the jetty. So the man is not successful. And we can't just say something like that without showing proof. We just show, well, he's 5 meters, 4.5. He's going to be short, 0.05 meters short. Okay? All right, guys, I hope that was helpful for you, and I'll see you in class next time. Bye.